So, as I said, no more quizzes. And so, I figured I would just use today's recitation to actually get a little bit farther in the lecture, maybe even free up some time at the end to do something fun. Well, fun for me, I don't know how you're going to feel about it. But yeah, let's just actually continue with series. And convergence. So far, we talked about telescoping series, we talked about geometric series, we talked about P-series, we talked about integral test. So, what are we on now? 5? Or did I start at 0? I don't remember what I started. Like number 5?
Yeah, I guess so.
We're on number 5 now. Okay. So we did everything I wanted to do for the integral test. I mean, there are many more examples that you can do, and we'll talk about that when we get to it. But the next test is called the comparison test. And it turns out, again, in a very similar way that we can actually compare improper integrals. It turns out the theory holds true for comparing to series, to infinite series. In fact, you kind of use the integral test to kind of show that this can actually work. So here's the idea. Suppose AN, BN are sequences with the following relationship. For any given term, the term of this sequence is always larger than the term of that sequence. Then it turns out that their sums would actually maintain the same inequality. Which makes sense if you think about it. I probably don't even want to specify what these guys are going to be, as long as they're the same. Their sums are going to keep the same inequality, because here we're adding up larger things, so it's going to be larger than if we added up smaller things. And so that should make sense. And moreover, I don't think I've ever seen that word used in a non-math concept. Like, who made that word up? Moreover, if there are two situations, well, technically 3 if you count them off, if the series of Bn converges, then so does An. Secondly, if the series of An diverges, then so does Bn. And this test gives you no info otherwise. And the intuition here is pretty much the same intuition that we built from improper integrals. So if this guy stops at a finite number, this guy's stuck between 0 and that number, he has to actually just stop somewhere eventually. You're just piling on, adding on numbers to this guy. He'll eventually have to stop somewhere. And so if this guy converges, that guy converges. Conversely, if this guy diverges, they're always larger than 0, so he's going to diverge off to positive infinity. This guy must always be larger than that. He's going to diverge also to infinity. In any other situation, though, you can't really tell. If this guy converges, this guy could still diverge, and this will be fine. And if this guy diverges, this guy could diverge or converge, and you can't really tell. So if you know one of these two particular relationships, you are able to make a conclusion about one of the series. Of course, the important thing here is you don't know ahead of time who you're going to want to pick to be the AN and the BN. Basically, on a case-by-case basis, you're going to look at a series and you're going to guess, does it converge? If you feel like it converges, then you think of you having the AN and you want to find the series BN that you know converges by some previous test or some other means. Or if you believe that it diverges, what you want to do is pretend that you have Bn you want to find some smaller guy that you know diverges. And if you can do one or the other, you can use what's called a comparison test, which we might shorten to say by comparison. So let's do an example here. And we'll do many more examples, but as we're going through the test, I'll only give one or two examples. And then we'll put them all together eventually. So k goes from 0 to infinity. 3k over 2k to the 5th plus 2k plus 1. If you had to guess, would you guess that converges or diverges? Okay, why?
I don't know, I just plugged in 0. Maybe I didn't get 0.
If you plugged in 0, what's going to happen? If you find the limit as k goes to infinity, it would be 0, but that doesn't really tell you it converges. What do you guys think? Yeah?
Like compared to the P series?
Which P series?
The 1 minus pi over 2, that'd be, like the top power is 1, like the bottom, the biggest power is pi over 2.
Right. Pretty much when things get out of hand is when you're going off to infinity for very large k. You don't know how small these guys are. Just as with limits, when it comes to series, the bigger guys control everything. So this series, its behavior is going to largely be controlled by the largest powers in the top and the bottom. So probably what you'd want to do is just ignore all the little guys and then really just focus on the big guys, which means that this guy is going to look like or behave like far off into infinity. I'll be adding terms that look like some constant times k over the radical of k to the 5th. Now that can be written as a p series, so that would be very convenient. So basically, if I try to compare 3k over this guy, 2k to the 5th plus 2k plus 1, and I'd want to compare that to this guy, what's another way to write down that? So that's like 3 over radical 2 times, what is that going to be? This is going to be 1 over k to the what? Right, so this would be 5 over 2, so it's 1 minus 5 over 2, and so that's 2 over 2 minus 5 over 2, so it gives you minus 3 over 2, so this guy is going to be 3 over 2. Next question, how do these two things compare? Can I tell who's larger, who's smaller? The one on the right is bigger, how do you know? This guy is larger because denominator here is smaller. So here, I just pretty much ignore everyone except the biggest guys, and I'm thinking that as we go off to infinity, they're going to behave like this guy. And I know exactly how one relates to the other. And in fact, notice here, so this would mean that if I look at the series, well, let me call this guy A N or K. Call this guy BK. Then it means that the series of AK is going to be smaller than or equal to the series of BK. And what can I say about BK? And does it converge? Yes. It's a convergent series with p equals 3 over 2, which is larger than 1. This means that the series of AK converges. And you would say by comparison. So you look at the series, first thing you check is the limit. This limit happens to go to 0, so the limit doesn't tell you anything. Next thing you're going to do, can I compare it to something? And it turns out just ignoring everyone except the biggest guys would give us something that I actually know is actually larger than this thing, and it converges. That allows me to use the comparison, or the comparison test. That's that. So now, next thing I want to talk about is a test very closely related to the comparison test, which really worries about this question. What if we don't know the inequality relationship between A and B? Which is a perfectly good thing to worry about. What if when I did this, I wasn't sure that that was bigger or smaller? Yeah.
With the P series, does it have to be limited infinity or can it be zero?
Oh, 0 would be a problem. So what we can do, yeah, good. I forgot about that. What we can do instead is just realize that this would be, if I plug in k equals 0, I would actually get 0 plus k equals 1 to infinity of that guy, and then I'll use this on from k greater than or equal to 1. It'll still work. Yeah, because you can't plug in k equals 0 here. So, yeah, but what if, again, I'm not sure who is actually larger or smaller, so I can't make a comparison either way. It turns out that there's another test that allows you to compare things even when you don't know which direction the inequalities would go in. This is called the limit comparison test. So this is basically used when you're not sure if AN is less than or equal to BN or AN is greater than or equal to BN. So pretty much you're in a situation where you'd like to compare two things because you kind of see, okay, if I ignore these terms, I can compare it to this thing, but I'm actually not sure which direction it would go in. Then the limit comparison test might be for you. Make a commercial then. Do you want to compare two series, but you're not sure what way to call the terms? It's all in like black and white. And then the limit comparison test might be here, and then it's all in color, someone using a limit comparison test. Yeah, we should do that. Okay. So here's how this one works. So suppose what we would do is we'd set up something. Set L equal to the following. The limit, and of course it's always as n goes to infinity, of an divided by bn. So we're going to take the ratio of the terms of the sequence. And here's what's going to happen. If L exists and L is greater than 0, and I want you to note here the an and the bn is not equal to 0. Because we're doing a division, you have to worry about division by 0. And technically you can take the ratio in any order, so it's not going to matter what order you take it in. Because if one way, for example, gives you 2 as the answer, the other one is going to give you a half as the answer, you'll actually get greater than 0 in either case. So just make sure you're not dividing by 0. We always have things that aren't 0. However, we compare their relative sizes of the terms. And the following holds. If we get a finite limit, that means one kind of behaves like constant times the other. And then, here's what you'll be able to conclude. The series of AN and the series of BN will both converge or both diverge. They'll both do the same thing. Once you take their ratio and let the limit go to infinity, if you get a number, it basically means that one is a constant times the other, or behaves like a constant times the other. So if one diverges, the other one's automatically going to diverge. If one converges, the other one's going to converge. So for example, let's say I take the limit of an over bn and I get a half. What that means is the terms of bn as I'm going off to infinity, they're about twice as big as the terms of an. If an goes to a finite number, then my bn is going to go to a number, not exactly, but roughly twice that number. And if my an goes off to infinity, my bn is going to go off to infinity. So we have that idea. This is called the limit comparison test. I want you to note that I don't care who's larger than who, so that is quite useful. Let me give you an example of that. So it might look very similar to the other one. So you had that series to do. What'd you guess, converge or diverge?
Divergence.
Why?
Because it's P series, but if you take the biggest ones, it's to the power of 1.
Alright, focus on that. Ignore all the little guys. It'll behave like 1 over n. We know that's the harmonic series that diverges. So I'm guessing that this is going to diverge. How do I prove it though? So the obvious thing would be I want to take n plus 1 over n squared plus 2n plus 3, and I want to compare that to, well, this n over n squared, which is 1 over n. And so now the question is, what's the relationship?
The one is less than.
How do you know?
There's the denominator, so it's smaller, that's it.
Denominator is smaller, so the fraction gets bigger. What happened to the numerator?
Oh, it changed.
The numerator got smaller, so the fraction is smaller.
So it's switched.
We don't know, right? We don't really know. I mean, you could go with some convoluted argument for why one might be bigger than the other, but then it might work for some n, not all of them. You'll waste a lot of time. It turns out you don't know if it's this or it's that, right? Because on one hand, we have a smaller denominator. So that means we should get a bigger fraction or larger fraction. And at the same time, we have a smaller numerator, which gives you a smaller fraction. So you made changes that simultaneously made your fraction bigger and smaller, and you're not sure who's going to win out. Now, rather than waste your time trying to figure out who's going to win, just not figure it out at all. So here, can't use comparison, at least not directly. It'll take a lot of work if you want to get it to her. So instead, what you are going to do is you are going to say call this guy AN, call this guy BN. By the way, notice that we know exactly what BN is going to do. So if this limit works out, I will also know exactly what AN is going to do. So L is equal to the limit of AN over BN. This is going to be the limit of n plus 1 over n squared plus 2n plus 3 times n. So this is going to be the limit of n squared plus n over n squared plus 2n plus 3, and that is huh? 1. 1 happens to be greater than 0. This means the series of AN diverges. We say by limit comparison. So I'd like to compare it to the harmonic series, but I wasn't sure which way the inequality turns, so I couldn't use a comparison test either way. Whenever you're in that situation, try the limit comparison. It might work out. As long as you have a limit existing and it's greater than 0, you will have that they will actually do the same thing. This is called the limit comparison test. So pretty much the fact that the limit is 1 kind of tells you that far off in infinity, both of these guys would kind of be adding terms that are roughly the same magnitude. And that is problematic for the harmonic series. Any questions about that? What test did I do now? We're going to have a bunch. And at some point I'm going to have you guys summarize all the ones that we're looking at. I do want to talk about that, but I'll probably save that for the end. Okay, so let's look at a test called the alternating series test. The name refers to the sign of the terms of the series, and basically it just means that the signs are alternating. So a series that looks like this, minus 1 to the n a sub n, where all the a n are positive, is called an alternating series. Note, it is so called because the signs will alternate. If you look at the series, say n equals 0 to infinity of minus 1 to the n a n, plug in 0. Every time your n is even, it's going to give you a positive sign, whereas every time it's odd, it's going to give you a negative sign. The particular n here doesn't really matter. It could be n plus 1, n plus 7, n plus 4. Doesn't matter. But the point is, it's changing the sign every time. So if I plug in n equals 0, I would just get a 0. But if I plug in n equals 1, I get minus a 1. Plug in n equals 2, I get plus a 2. N equals 3, minus a 3, plus a 4, and so on. So notice that the signs are alternating. And we require that our terms without this part is positive because I want to guarantee that signs are alternating. If they were allowed to be negative or 0, what can happen is if a negative coincides with a negative, I'll have a list of positive signs in a row and it won't be alternating at that point. So to guarantee that it is alternating, we make sure that this part is always going to be positive, or we have some other factor that's changing signs. This is called an alternating series. And we have a test for alternating series, and it turns out it's actually really nice, actually. Because in that case, the limit of the sequence actually tells us a lot of info. Now, the alternating series test. Let this be an alternating series. If there are three conditions: one, an are all greater than 0. 2, an is decreasing. This was also mentioned for the integral test, but I do think I don't think I actually described what that means. So, what does it mean to be decreasing? There are a couple ways that you can show this. One, this means that each new term is greater than or equal to the previous term. That's the other way around. Right? So each new term is less than or equal to the previous term. That means it's decreasing. And 2, so if you can actually show that, if it's obvious when you plug in n plus 1 for all the n's, you get something that's smaller. You can show that. For example, for the harmonic, if an is 1 over n, that would be obvious. 1 over n plus 1 is going to be smaller than 1 over n. It's pretty much obvious for you to just state it. And 2, another way you can show this is to actually just use calculus. Find the derivative of an, show that it's less than 0. So you can show by this or by that. Now, for the most part, you should make sure this is true. If you're using the alternating series test and you just pretty much just state that an is decreasing, I'll probably believe you. Okay? Just make sure you're right. Okay? Don't say something's decreasing and it's actually not decreasing. I'm like, you don't know what you're talking about, dude. You're just trying to pull one over on me. You say it's decreasing and you're right. Then, okay, the kids need help too. They probably can know that it's decreasing. Okay, so if it's decreasing, and finally, so we have decreasing terms, which I can verify by one of these two, and at the same time the limit of an is equal to 0. So the terms are decreasing to 0. If these three conditions are fulfilled, then this guy converges. If those three conditions are not fulfilled, I can't use this test. I have to use something else. It might converge or diverge. But if I'm looking at a series that has alternating signs and the terms are decreasing, right? If I ignore the signs, all of them are, if I ignore this part, all the terms are positive, they're also decreasing, and they actually decrease all the way to 0, we will have convergence. It turns out that if you find out in the case that the limit does not approach 0, then minus 1 to the n times that thing is also not going to be 0. So you could just actually use the test for divergence. But let's say the limit is 0, but these, you don't necessarily have decreasing. You have things bouncing up and down a little bit. You're probably not sure, so you should do something else. But this is called the alternating series test. I think I just have a silly example here, because they're kind of nice to work with anyway, if you have an alternating series. Example. Famous example, the alternating harmonic series. This guy actually converges. So if you look at the series of minus 1 to the n over n goes from 1 up to infinity. Memory serves that converges to ln2, but we'll probably actually compute that at some point. To show you 1 over n squared, the sum of that converts to pi squared over 6, we'll probably need stuff outside of Calc 2. But this is something you can actually prove with the stuff I'll be telling you in Calc 2. So, you will say, note, we have minus 1 to the n, a_n, where a_n equals 1 over n. And you would say a_n is larger than 0 for all n. And you will tell me a_n is decreasing, which again should be obvious here. The only time I'd say is justifies if it's really like crazy looking and there's no reason for you to just see that it's decreasing. You probably have to do a little bit of justification. And lastly, if I take the limit as n approaches infinity of a_n, this is the limit 1 over n, that is 0. Therefore, this guy converges by the alternating series test. Its positive decreasing limit is 0. And the signs are alternating. Pretty sure this actually converts to ln2, by the way. Just a little fact. We'll actually prove that. So you take 1 minus a half, plus a third, minus a quarter, plus a fifth, minus a sixth. You do that forever, it adds up to log 2. Yeah?
If it was going to start with a positive one, then would you have to do that plus one?
Come again?
If you're going to start with positive one, you have to start with n plus one. As an example.
Yes, if you wanted to change the signs, do I want it to start with a 1? I think I do want it to start with a 1. So I'd probably do plus 1. But yes, if you wanted to change the sign, I think it's with the minus 1 converts to ln2. We'll actually do that. So the other way it would convert to the negative of whatever it was before. Yes, you can actually alter how you want the signs to move by say adding a 1 here or something. Let's do yet another test. This one's actually pretty cool, and we're going to use it in many more case situations than just proving a series convergence. It is called the ratio test. So it's very widely applicable, pretty much any series with non-zero terms. It's the only restriction, really. I will mention it's particularly useful in certain situations. So if you see a bunch of things like with factorials and exponential functions, and general exponential functions, not necessarily just e to the n, but other ones. This test is particularly useful in those situations. Probably just not rational functions though. Or, okay, so we have any series like that. Then, if we set, I'm going to compute another limit. Let's write it out over here. L equals the limit, obviously as n goes to infinity, of an plus 1 divided by an. It's called the ratio test because we take a ratio. People are also naming things. Okay, so you find that limit. Now it turns out that this one has several cases. If your L is less than 1, okay, so you find this limit and you realize that it's less than 1, the series converges. More important than that, converges absolutely, absolutely converges. That's going to be a very good thing for us to know. When a series converges, does it converge absolutely? If L is larger than 1, the series diverges. Basically, that's saying each successive term is going to be larger than the previous term. 2. If L is specifically equal to 1, then no conclusion. By the way, this will happen for any rational function. So don't waste your time. Right, you see a rational function, probably the best thing to do is a comparison with a p-series. Either limit or regular comparison. Right, because if you replace all the n's with n plus 1s, the degree of your polynomials aren't going to change. So the degree of the numerator and the denominator will always be the same thing. The limit's always going to actually give you 1. And that doesn't actually tell you anything. No conclusion can be made. It's easy to see that no conclusion can be made because L would equal to 1 for both the series of 1 over n from 1 to infinity and the alternating series of 1 over n. And we know that this one diverges while this one converges. So if the limit is 1, it doesn't tell you anything. It's called the ratio test. Now you can really get crazy on this one, but let's do 2 examples. That one. And yes, it's the first example, so it's kind of easier than probably one that you will see in general. So I would just mention here, the alternating series test actually works here. So if I just ask you about convergence, probably you'd use the alternating series test. All those terms are going to be positive, and we have a polynomial on top of an exponential. You should know that the limit is going to go to 0. That's definitely decreasing. However, the benefits of using the ratio test as opposed to the alternating series test is that the ratio test tells you about absolute convergence, which is a very important thing to know about. But alternating series tests won't tell you about absolute convergence. So let's say, for example, here, yes, we can use the alternating series test, but let's suppose it was really important to me to know that it converges absolutely, meaning even without the change in sign, would it still converge? That would be something that we want to consider. So what we can do is I can set this guy equal to my, or even the whole thing, equal to my an. I would compute the limit of an plus 1 over an. Notice that that is going to be the limit in absolute values of, I'm just going to replace all n's with n plus 1s. And then I'm going to divide by that thing. Dividing by that is the same as multiplying by the reciprocal. So this part here is 1 over an. Now, here you can probably see what's going to happen, but in general, probably what I like, what you should do, what I like to do is kind of separate the different kinds of terms. So I'll put the minus 1s together. I'll put the polynomials together. And then I'll put the exponentials together, right? It's going to be easier for you to see what's going to happen. Now, of course, this is going to cancel with that. That's going to give you a negative sign. The absolute value is going to kill it anyway. So I can essentially ignore this negative. It's always going to happen. So whether you choose to take the negative or not in the first place, it doesn't matter. Secondly, I realize that the limit of n plus 1 over n, that's going to approach 1. What about the other one? It approaches 1/2, because this is going to cancel to that. So this is going to approach 1/2. And so it turns out that this limit equals 1/2. 1/2 is less than 1. This means the series converges. Not only does it converge, it converges absolutely. Just to make sure. Do we know what n factorial stands for? Guys, we talk about that yet? Alright. That means 1 times 2 times 3 times all the way up to n. So, for example, 5 factorial. It's not fun. It's just 1 times 2 times 3 times 4 times 5. It's not someone getting excited. It actually means something in mathematics. It's 120. So you deal with that a lot in probability statistics, but I don't know if I remember if I mentioned it for you guys. So it's not n, it's n factorial. It's red, n factorial. So for integers, that's what it looks like. You can actually define the factorial function to work on any real number, but you would need complex analysis to do that, and something called the gamma function. So we won't talk about that. Here we only care about plugging in integers, though. What can you tell me about this series? By the way, this diverges. I know that by test for divergence. First thing you should look at any series. Factorials are larger than exponentials. Also something I mentioned before, logs grow slower than polynomials, grow slower than exponentials, grow slower than factorials, grow slower than something like that. So I mentioned this in Calc 1 as well, but we never really experienced these two guys. Now you can experience them. But we'll use the ratio test. even though I know it's going to diverge. Let's just actually see how it would shake out here, just for practice sake. Because it's worth you seeing, actually going through the calculations here, how you would deal with a factorial, what that actually means. So, if I set L equals to the limit of an plus 1 over an, this is going to be, again, I can ignore the negative sign. This is going to be n plus 1 factorial over e to the n plus 1 times the reciprocal of that. I will put these guys together. And what can you tell me here? What happens to this guy? Just goes to 1 over e. Right, so that just goes to a constant. And to this guy, it goes to n plus 1. So n plus 1 times 1 over e. How do you see that it goes to n plus 1? What does n plus 1 factorial mean? It's just you multiplying all the numbers all the way up to, say, n minus 1, n plus 1. And of course, n factorial means you're multiplying all the numbers up to n. 1 times 2 times 3 times n minus 1 times n. Notice that one's going to cancel out, except that guy. This is just n plus 1. Okay? And things like that you should be used to when computing factorials. What is what's that equal to? Then the next thing would be n minus 1, counting all the way down, but then the denominator is going to cancel all that. So this here is actually just a really fancy way of writing this quartic polynomial. Okay, so I want you to see that with factorials, how they work out. Pretty much you just imagine them being expanded forever, and then you just cancel out the common terms and write what you're left over with. So that would be that. Now 1 over e is just a constant, and as my n is going to infinity, what's happening to this guy? Well, that's going up to infinity. So this implies that our L equals infinity, which you might notice it's larger than 1. It diverges in spectacular fashion. Ratio test. And we'll stop there today. We have one more test to cover. Then I'll tell you some stuff about the test, how useful each one is, and then we'll cover some applications. Let's talk about power.